Energy. So here's where it just gets boring and we do straight up chemistry stuff. You want to know the difference between kinetic energy and potential energy. It's not really all that important for us. For us, what we want to understand is one particular form of potential energy, which is chemical energy. And for us, that is the energy that is stored in the bonds of chemical substances. And it gets released when bonds are broken and reformed. So when we're looking at molecules and we see the little bonds between atoms in a molecule, we're thinking that's energy. There are other forms of energy like electrical energy, which you're familiar with and our body uses, mechanical energy, which our body uses, and radiant energy, which is primarily the electromagnetic spectrum, of which light is a part, infrared, X-ray, all of that. But matter, because we're talking about our bodies and our bodies are made of matter, that is what we're going to spend most of our time talking about. This phrase comes from the old Merib textbook. It is the stuff of the universe, anything that occupies mass or has mass or occupies space. All matter is made up of elements, and without looking at atoms, it's a little tricky sometimes to define what an element is. But it is something, as it says here, that cannot be broken down or purified further while still maintaining its original chemical and physical properties. So these are things like its reactivity, its melting point, its boiling point, its malleability, its color, its texture, all of that stuff. All elements are composed of atoms. So an atom is the smallest amount of any element you can have. And once you get something smaller than that, then you're dealing with subatomic particles that no longer have the properties of the element, of the atom from which they came. So all of our elements have atomic symbols. Like for oxygen, it's O. This is a chart of most of the most common elements found in the human body. So you really should commit all of these chemical abbreviations to mind. Most of them are easy enough to remember, with the exception of potassium, which is K. I forget where the K comes from. And sodium, which is Na, because it used to be natrium. So if something, I won't get into it, natrium. Iron, Fe, used to be ferrous or ferric material. That's where that comes from. Then the atoms are arranged in what we call the periodic table of the elements. And I think what I'm going to do is pause for a second, or tell you that you should pause and watch this video on the periodic table, because it's a little bit of history. It's pretty cool, and it's an introduction to Crash Course, which there's a whole Crash Course for Anatomy and Physiology series on YouTube that you could get for free, like your own private tutor. Welcome back. What does everybody think of Hank Green? Right? He's pretty entertaining and rather knowledgeable. If you did watch it or if you didn't, just to sum up, what they found out, what Mendeleev's and others found, was that chemical properties of elements repeat themselves every once in a while, and there is a period to that repeatability. So instead of just arranging things by increasing weight, they put them in this table. So this group of elements here, hydrogen, lithium, sodium, potassium, all have similar chemical properties. And beryllium, magnesium, I don't know what K is. It's not cobalt. There's cobalt. See, oh, calcium. Oh my God, how could I not know calcium, right? So when you arrange them by period, you end up with columns of elements that all have similar physical and chemical properties. And again, those properties repeat themselves periodically. And we are going to get to just how mind-blowing of a thing this is in a few minutes. One of the things you need to understand before we move on is that Mendeleev and all the other people that were sorting things by chemical properties did not know what atoms looked like yet. I do believe like the concept of an atom was known, but the whole idea of what they looked like, nobody knew anything about electrons, neutrons, protons, and all that stuff. Okay, so what do we now know about atoms that Mendeleev did not know? There are different ways to illustrate atoms. We are going to use this planetary model because it's a little bit easier to understand, especially when it comes to counting electrons. The electron cloud model or orbital model is a little bit more accurate in terms of how electrons are actually physically arranged in an atom, but it doesn't help us understand things, so we're going to stick to this planetary model here. All right, we are going to start our tour of the atom in the nucleus, this part here in the center. There are two kinds of subatomic particles in the nucleus, neutrons and protons. Protons are called protons because they have a positive charge. The magnitude of that charge is just 1. I don't know that there are units. It's not like millivolts or anything. We just give it a charge of 1. And we also give it a mass of 1 atomic mass unit. I'm sure somebody has worked out its mass in grams, but it would be an infinitely small number. So we just say whatever a proton weighs, that's 1. Neutrons are called neutrons because they are electrically neutral. They have no charge, but they have the same mass as a proton, 1 atomic mass unit. Then out in the cloud or the orbitals are electrons, which we generally think of as being arranged in shells. They're really energy levels or energetic states at which they exist. The electrons have almost no mass. They do have mass, but the mass is so small that even super picky people like chemists who pay attention to detail basically just say, look, let's call them 0. It's not worth counting the mass of an electron. They are equal in number to the protons in an atom and have a charge of -1, so equal in magnitude to the protons, but opposite. So an atom in its elemental form is going to have no net charge. It'll have the same number of protons as it has neutrons. We sometimes refer to the atoms by their atomic number. So that's the big number here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is the number of protons. And then if the atom is in its elemental state, that is also the number of electrons. Now we need to look at these electron shells or energy levels as they are called. So you start, the smallest atoms, helium and hydrogen, have just this one inner electron shell that has room for 2 electrons. If you have more than 2 electrons, you start a second energy level that can hold up to 8 electrons. So here is carbon with 4 in its outer ring, and neon has 8. Its outer energy shell is full. So the second shell, if we put, the third shell, if we put another one around neon, would also hold 8. If we added a 4th shell, that would hold 18. Now, let's go back to our periodic table. First row of the periodic table, 2 elements. Second row of the periodic table, 1, 2, 3, 4, 5, 6, 7, 8 elements. Third row, 8 elements. Fourth row, 18 elements. So what's happening here is the period is related to the filling of the electron shells. So if you have, as you add electrons to your shell, your outer shell, your chemical properties are changing in a periodic fashion. And then when you start another energy level, you start another row on the periodic table. And as you add electrons, the physical and chemical properties of that element change in a predictable fashion, till you get down to this fourth row here, which has that 18 electron energy shell. So what Mendeleev and others did, without even understanding atoms, is arrange the atoms according to their subatomic structure. Boom! Your mind should be blowing right now, like gray matter splattered on the wall behind you, right? So structure function applies even at the atomic level, right? The chemical properties of a given atom, what it's going to react with and how much of what it's going to react with, are derived directly from its subatomic structure, how many electrons it has in its outer energy shell. It is just the coolest thing ever about science, and I never appreciated it until just 4 or 5, I don't know, maybe 10 years ago. It just dawned on me how mind-blowing that is, at least for me. Moving right along, now that our minds are no longer blown and we're just going to get back into boring chemistry. Mass number, I'm not going to ask you about, but we'll talk about it really briefly because it makes the world more interesting. As we said, atomic number is just the number of protons. The number of protons in any element is fixed. However, you can have different numbers of neutrons in an element. So here is regular old hydrogen. Hydrogen just has one lonely proton in its nucleus. Why it doesn't have a neutron normally, I don't know. You can have deuterium, which is now hydrogen with one proton and one neutron, or tritium, hydrogen with still one proton because the number of protons defines what the element is, but now it's got 2 neutrons, so its atomic mass is now 3 instead of 2. So it is heavier hydrogen. Because the electrons determine the chemistry of the atom, all of these atoms are chemically hydrogen, they just have different masses. So this is where isotopes come from. These isotopes, well, I should say H1 and H2 are stable. Tritium H3 is not stable, which means occasionally one of these protons is going to leave, and that produces a little bit of radioactivity. I forget what kind of particles or what kind of radioactivity tritium releases. I think it's like a really weak alpha emitter, which means it doesn't do a lot of damage. But we can take advantage of radioactive forms of radioactive isotopes of different elements to make different imaging techniques. This is a PET scan, positron emission tomography. Don't ask me what a positron is, I just know that it's a form of radiation and you can detect it. So they basically use radioactive glucose, I believe, that the patient ingests, and then those organs that are more highly, no, actually not, yeah, those organs that are more highly metabolic are going to have more of that glucose. And so you can label highly metabolic organs with the radioactive glucose and see tumors and stuff. All right, moving right along, right? So we were talking about these electrons. It turns out that most atoms in their elemental form are not chemically stable. They're not happy with the number of electrons in their outer energy shell. They are more stable if their outer shell has 8 or if their outer shell is empty. And I just want to show you one thing. If we go back here, right? Here's outer shell not full. These are all outer shell full. These are your noble gases. So the reason why they're called noble gases is that they don't perform a lot of chemistry. They don't react with other elements. And the reason why they don't react with other elements is their outer energy level is full of electrons, so they don't do chemical bonds because they don't have to. So all of your other elements want to change the number of electrons in their outer energy shell to either fill it or empty it. There are 2 different methods they can try. They can share electrons with other atoms, or they can donate, get rid of an excess electron or 2, empty their outer orbital, outer energy shell, or they can pick up some excess electrons here. Whoops, I'm clicking too much. And fill that energy shell. Either one of these two things results in what we call chemical bonds, or intra-atomic bonds. So these are bonds that hold two atoms together. There are going to be three different kinds of bonds you need to know about: covalent, ionic, and hydrogen. We will point out later that hydrogen bonds do not hold two atoms together. They're actually intramolecular bonds, so they're bonds between molecules, but we still talk about them with the other two bonds. So for these, what you want to concentrate on is how does the bond form, what makes a covalent bond, what makes an ionic bond, what makes a hydrogen bond, and which one is strongest, stronger, weakest. So they're listed here in order from strongest to weakest. Covalent bonds are very strong. Ionic bonds are relatively strong. And then hydrogen bonds are very, very weak, but still very, very important. So starting with covalent bonds, this is the type of bond that forms when two atoms decide to share their outer shell or valence shell electrons. The valence shell is the outer energy level shell. So here you have hydrogen. Hydrogen has one lone electron in this small shell that can fit two. So it wants one more. What it can do is get together with another hydrogen, or really any other atom, and share electrons. So now both of these hydrogens kind of sort of have two electrons in their outer energy shell. It's not perfect. They don't both have a full energy shell, but sharing electrons is better than not having those shared electrons at all, or excess electrons at all. Here we have oxygen. Oxygen has 6 electrons in its outer energy shell, so it needs to pick up 2 more, or share 2 electrons. So here there are 2 molecules of oxygen that are each sharing 2 electrons with each other. So this is what's referred to as a double bond. To show you a single bond, let me just skip ahead. Right, here's our friend water. Here are 2 hydrogens that each need 1 covalent bond. They need to share 1 electron each to be happy. And here's oxygen that wants to share 2 electrons. So oxygen gets together with 2 hydrogens, makes a covalent bond with each hydrogen, and now the oxygen has 2 electrons that it's sharing with the hydrogen, and each of the 2 hydrogens have an electron to share with oxygen. Let me go back up here. And then, so this is a double bond, and these are also double bonds here. Carbon has 4 outer shell electrons, so it needs to form 4 covalent bonds, or share 4 electrons. What it's doing here in CO2 is making 2 covalent bonds with this oxygen and 2 covalent bonds with that oxygen. So the 2 oxygens are happy with 2 electrons that they're sharing with carbon, and the carbon in the middle is happy because it's sharing 4 electrons, 2 with each oxygen. So covalent bonds come in different flavors. They can be nonpolar or polar. Nonpolar means that the 2 atoms in the bond are sharing the electrons equally. So carbon and oxygen are examples of atoms that form nonpolar covalent bonds. So these 4 electrons that are being shared between oxygen and carbon in this double bond here are being shared equally. So they're spending just as much time near oxygen as they are near carbon. And if we remember, atoms don't have a net charge, so if atoms share electrons equally, you're still getting an even distribution of electrons that cancels out all of your protons, so there are no positive parts or no negative parts to this molecule, no positive or negative poles. A polar covalent bond forms when atoms do not share electrons equally. Oxygen here has a much bigger nucleus than does hydrogen, so it is better at attracting electrons. It is what is called more electronegative. So the electrons that oxygen shares with hydrogen are going to spend more time closer to oxygen than they do spending close to hydrogen. So if you have electrons from hydrogen that are spending more time near the oxygen, then their charge is going to start showing, because it's going to look like the electrons in this oxygen molecule outnumber the protons because of those electrons from hydrogen. And here now, hydrogen's electrons that usually just spend time around hydrogen's nucleus are now spending more time closer to the oxygen nucleus, and hydrogen's electron is therefore not counteracting or not neutralizing the positive charge on the proton in the hydrogen, and the hydrogen portion of the molecule takes on a partial positive charge. So this little Greek letter sigma means partial. So these are two partial positive charges, these are two partial negative charges. So if you have a negative end and a positive end of a molecule, those are called poles. So this is a polar molecule formed by a polar covalent bond. And you are going to see that these end up being very important later on. Next up is ions, which is going to lead to ionic bonds. So chlorine in its atomic state has 7 electrons in its outer energy shell. It just needs to pick up one more to be awesome or energetically stable. So what it does is it just finds an electron floating around in the world. It fills its outer energy shell. Now you have chlorine with an extra electron, so it's got a negative charge, or a charge of -1 now. It is now called an ion, because it is no longer in its atomic state, its elemental state. It is an ion, and it has charge. As you may know, right, charges interact with other charges, and this is where ionic bonds come from. They don't show it very well, but sodium, let's go up here real quick just for fun. There's sodium right there. Sodium is in the first spot on the on its row of the periodic table, which means it's just got one lone electron in its outer energy shell. So what sodium usually does is just let go of that electron, become a sodium ion, and it takes on a charge of +1 because it now has one more proton than it does electrons. So when sodium ions and chloride ions find themselves next to each other, you have a positively charged ion next to a negatively charged ion. Opposite charges attract and they stick to one another. And this is how ionic bonds are formed. Now the way they're showing it here, they're showing sodium donating this electron to the chlorine, but it doesn't have to work that way. It doesn't matter where this electron goes. It doesn't matter where chlorine gets its final electron. It could be from another atom, or it could just be floating around in solution. It is not the donation or moving of the electron that causes the bond. It is the change in charge, or the opposite charges that become attracted to each other, that make the bond. So those are ionic bonds, the attractive forces between oppositely charged ions. Now, we said earlier that ionic bonds are not as strong as covalent bonds. And this is going to then lead to our hydrogen bond. So here you have some salt. Here you have some water. If you put salt in water, you all know what happens. It dissolves. What that looks like when it dissolves is the sodium and the chloride ions dissociate from one another, and you have sodium with a hydration shell, a group of water molecules around it that each have their partially negatively charged hydrogen oriented towards the sodium, and the chlorine has all of the oxygens around it with their hydrogens pointed in. So the ability of water to form these weak bonds with the sodium and the chlorine is what causes the sodium chloride to dissolve. If this were covalent, water wouldn't be able to do that, or it's not strong enough to break covalent bonds. So what we're seeing here is an example of a hydrogen bond. As this says right here, it is the attractive force between partial charges on polar molecules. So if you have a polar molecule, like water, its negative end is going to be attracted to positive things. Its positive end is going to be attracted to negative things. Those weak attractive forces are what make up hydrogen bonds. And because the two atoms in the polar bond are part of a molecule, right? Hydrogen bonds generally take place between molecules, and sometimes even inside of large molecules. They're part of what hold DNA and protein together. But we tend to think of hydrogen bonds mostly as existing in water. So this is water molecules hydrogen bonded to one another. Water is a really special molecule, partially because of its atomic structure, its shape, the shape of the molecule, and partially because of its great ability to form hydrogen bonds. And it's got a negative end and a positive end, so it can hydrogen bond with both positive and negative things. Water molecules, when they're together in solution, hydrogen bond with one another, so all the oxygens are oriented towards hydrogens and all the hydrogens are oriented towards oxygen, and it's sort of a fluid crystalline structure. This is an example of intramolecular bonds, or hydrogen bonds taking place in between two different parts of a very big molecule. So this is supposed to be a peptide chain or a protein. It's a long string of amino acids. Here you have a positive charge up here. Here you have a negative charge down there. If you fold this thing over, you can bring that charge into close proximity to this charge, like you have right here, and form this bend. So it's hydrogen bonding between different portions of a long protein chain that allow proteins to fold up into the shape that they take in their mature form. We haven't gone over proteins and DNA yet, but I'm just giving you an example. You may or may not be familiar with the DNA double helix. It is two phosphate backbone chains with bases held together by hydrogen bonds. So this ribbon here and this other ribbon there, those are two separate, very long, very large molecules that stay stuck to each other in this double helical shape because these bases in the middle, all of these yellow things, hydrogen bond with one another. So the whole concept of heredity, our DNA, which gets passed down from generation to generation to generation, works because of hydrogen bonding. So the importance of hydrogen bonds in biology cannot be overestimated. And I think we're going to stop there, and I will do a second video for water and solutions, and there's already one up there for macromolecules. This one's getting just a little bit long, and I don't want to run over.